Hello and welcome to the final unit of AP Statistics, Unit 7, which is Inference about related variables. Topics we'll cover in this unit are chi-square testing and linear regression model. Like the previous two units that deal with their own testing, this will also contain hypothesis testing as well as confidence interval for both chi-squared and linear regression model. To begin, we're going to discuss what chi-square test means. It just means a test to determine how closely the observed value fits the model. Basically, how closely do the values we observe exist with the values we predicted. A cell is a certain value in a table. The table I will show you very shortly. Chi-squared statistic is a statistic to test whether the observed counts in a distribution match what we would expect. So again, it's to determine whether what we got is similar to our model. It is represented by this. Although it looks like an x squared, there's actually chi. So chi squared is equal to the sum of all our observed minus expected squared divided by our expected. And now since it's squared, the values are always going to be positive. Standardized residual is the residual for each cell. Now I don't know if you can see this, but if you look at this relationship and this relationship, this standardized residual is just the square root of the chi-squared for a single cell. Now we move on to what the table is. So as you can see, this table over here, let me enlarge it for a second. Table over here is a good example of what you could see on your test. So here we have our variable, which is age group, and another variable, which is yes or no. I will discuss what the conditions are to have a chi-squared test. Now let's look at this. Now if I wanted to find the chi-squared, my chi-squared statistic, I would have to know what my expected value is for each one of these cells as well as my observed, and same goes for my standard residual. Now if we look at this thing where we'll read it as row comma column, so 18 to 34 comma yes is 231. So that is my cell value for 18 to 34 comma yes. That'll be over here. Now we're going to look at the table over here. As you can see, there are these three things over here: goodness of fit, homogeneity, and independence. These could just be three arbitrary terms to you, but to a statistician, these are your three types of chi-square testing you will see on your AP Statistics exam. So firstly, what do these tests mean? When can you use them? What are your conditions? What are degrees of freedom? What are your expected value? Your null hypothesis, your alternate hypothesis, and below that I have your calculated controls. Now let's look at definition. Goodness of fit chi-square test is a test to determine whether the distribution of counts in one variable matches the prediction of the goodness of fit. Now what does that mean? It means, did what we expect come out to what we observed? Homogeneity is comparing the distributions of counts for two or more variables. Or in this case, we would say not variables, rather populations. And I'll explain why. So this is comparing whether two populations, or sometimes more, but generally two populations, whether or not the distribution is same. So for example, you could get a question such as class A had an average test score of, or their scores range from 4 to 7, let's say, but class B scores ranged from 6 to 8. Is this difference statistically significant, for example? Next one, independence. You could try this out for yourself and see if you understand what independence means, but it just means a way to determine whether or not two categorical variables are independent or not. And why do I say the word categorical variables? It just means that the only way to test whether the only way to use a chi-square test is for categorical variables, which may seem odd because we're assigning them a value, but that is what it is. Now, when can you use a goodness of fit? This is going to come up a lot because sometimes you'll see goodness of fit and homogeneity and you'll think, oh, I can use goodness of fit or homogeneity. Let me just go with one or the other. No, but there are certain conditions as to when you can use them. So we're going to say that goodness of fit is when one variable and one population is given to you. Homogeneity is when one variable two populations are given to you, and for independence it's two variables, one population. As you can see, these numbers are just ones and twos, so this generally or more statement generally does not come up on the AP exam. So you just need to remember goodness if it is 1 1, which is very simple to remember. Homogeneity, or you can actually remember independence and then you remember homogeneity. Independence is when you're checking for two variables whether they're independent or not. Now the conditions are same for all three of these. This is counted, categorical, SRS, and N is less than 10%, and your expected counts are greater than or to 5. We've seen this SRS and N multiple times already. Now I'm going to copy this so you guys get a better understanding. What do I mean by counted categorical? If you look at the table above, you see that all these numbers are whole numbers, or they're integer numbers. Their values greater than or equal to 0, and they're not decimal representations. Because how can the number of people who voted yes in the age group 18 to 34 be 224.6? You can't have a decimal value, and that's why it's counted. But categorical, why does it have to be categorical? You have to make sure that it's categorical so that you can assign multiple values to it. If we had, for example, weight over here instead of age group, we couldn't define a single value here. Like, how can you have yes for weight group of 15 or weight of 15 kilos? You'd have a long list here. So to make that easier, we would keep it categorical. However, you can put something like weight group here, and then you would have 30 kilos to 40 kilos. Because if you look here, age is quantitative, but age group is categorical. So you could go around in that regard. Now expected counts are greater than equal to 5. Again, what are expected counts? They will tell you the entire sample population or the entire sample size, and from there they will clearly indicate what the expected value would be for a question that contains goodness of fitness, a goodness of fit test. So that's nothing to worry about, but you just remember that it has to be greater than or equal to 5. Even if it's a decimal, even if it's 5.0001, it counts. Now for degrees of freedom, generally we've learned that it's n minus 1, which is the case for a goodness of fit test. However, for homogeneity and for independence, it's a bit more different. It's row minus 1 multiplied by column minus 1. Now what does that mean? It just means the number of rows minus 1 times the number of columns minus 1. So for example, in this case, if we are using a test of independence, we have 1, 2, 3 rows and 1, 2 columns. So our degrees of freedom would be 3 minus 1, which is 2, multiplied by 2 minus 1, which is 1. So our total degrees of freedom would be 2. That is also important to remember. Now expected value. Why have I blacked this part out? Is because you don't have an expected value as a given formula. It is just what you have to get from a question. So for example, a question could be like two-way table, again, with the number of siblings. So either you could have 0 siblings or 1 sibling, and the proportion of people. And they tell you 50 people were selected for the trial. So my expected value of each one of these cells, I'm going to put it down here. So this would be my expected count, for example. So my expected count for the number of people with sibling would be, but not multiplied by 0, rather multiplied by 50, because that's the number of people in my trial. So if you wanted to, you could think of it as proportion multiplied by n. And same goes for this, you would have 0.8 multiplied by 50. And that's how you get your expected counts. Homogeneity and goodness of fit, it is this monster. It is your row total times your column total divided by your grand total. So if I wanted to find the expected value for this 18 to 34 and my yes, I'd find row total, which is 972, multiplied it by my column total, which is 2191, and divided it all by 8866. And similarly for 35 to 54, no, I would go 35 to 54, my total is 2911, my no total is 6675, multiply these together and divide by my grand total, and that would give me my expected value. Now for null and alternate hypothesis, for two of these, they're the same. Maybe you could guess which ones they are. Pause and see if you can figure out which ones they are. So if you did or you didn't figure it out, doesn't matter, we'll look at it. So for goodness of fit, the null is that the distribution, sorry, I don't see why there's an issue right now. The distribution is as stated. I'm just going to copy this onto this because for homogeneity, it's the same thing. The distribution is as stated. Now for independence, you're going to, okay, it's shaking too much. I'm going to pause it. I'm going to fill it in and then I'll come back. Fit and homogeneity, these are your null and null and alternate. The distribution is as stated, the distribution is not as stated. For independence, it is that the variables are independent and the alternate is the variables are not independent. Now in the previous video, I may have mentioned why we don't say they are dependent. Because just because you're not independent does not mean you're dependent. You could just be independent but not dependent on anything. You could just be two coexisting trials or whatever. Now for calculator controls, again, these are on the TI Inspire. So for goodness of fit and homogeneity, very similar. You create a list of all the observed values, and then for all the expected values you can actually get when you do stat.exp. I will show that on my TI. Then you just go menu, stat test 7, chi-squared goodness of fit 7. Then you insert the name of your observed value list into the observed list, expected value list into expected list, and degrees of freedom. Sometimes they may give you degrees of freedom, other times you're going to have to figure it out from the formula given here, which would be a row -1 times column -1 or n -1. For independence, you'd have to create a matrix. So this is the one where you can do expected values without actually having to create an expected value matrix. So you first do all of this, you do menu, stat test, chi-squared two-way test, and then you observe, and then you insert the name of your observed matrix. Now if you want to find expected value matrix, expected value matrix, you would, once you create your original matrix, so create matrix, the very next thing you have to do is you have to do stat.exp on that matrix. Stat.exp matrix, but you can only do this once you have done your chi-squared two-way test, which is the only issue. So create your test, create your matrix, do your test, and then you can continue to do, and then you can find your expected value matrix. That will come up eventually in your exam. So if you ever see a question that refers to doing a chi-squared test of independence, I would suggest doing your test first and then checking conditions. But when you write it down on the paper, write down conditions first, because that will make it a whole lot easier. Now we'll take a look at linear regression. It's just another way to test whether two variables have an association. For this one, your degrees of freedom are n-2, where n is the number of your data points. You may have remembered in Unit 2 when we discussed linear regression. This is very similar for that. Now, the conditions for using a linear regression test is that the form of the relationship is linear, and if not linear, just very approximately linear. They're independent. One thing I forgot to mention with the chi-squared is that you don't have to test for independence, because in this case, based off the SRS, you would assume independence, but you should also write independence as one of your conditions. I'm going to change that so in my solved notes you'll be able to see that. And finally, you have to always make sure that your data is approximately normal. This generally ends up being a condition for everything. And one way to test that is where when they give you the linear regression the question, they will always accompany it with a scatter plot. So you look at the scatter plot to determine whether it's approximately linear, whether it's approximately linear, how normal it is, and independent will be given in your question. So when you're doing a hypothesis test, your null is that there's no association between variables. Sometimes you refer to it with the line, and you always say that beta for your null is equivalent to 0. I would always write this down on my test just so that in case I get a grader that doesn't like words, they can also refer to my symbols. So what will our alternate be? We've done 2 units of hypothesis testing so far. Maybe you can pause the video and try it out yourself. So your alternate is that there is positive, negative, or some association between variables. Now you've heard of positive and negative association. So association you would have where beta is greater than 0. For negative association you would have beta is less than 0. But what does this sum association mean? Sum indicates that the question is ambiguous of whether or not it's positive or negative. So what do you put for beta? I generally left it alone, but some people tend to write it as beta equal to 0. I never like that because it's so ambiguous and it was just too ambiguous for me to write. So when you're talking about sum association, you can always leave out this beta in 0 part. It's perfectly acceptable. Next, we're going to do a t-test. So what does the t-test mean? So when they ask you a question, they generally say conduct a hypothesis test or a t-test for the slope of the thing, the slope of the variable, the slope of the graph. So that's why you have b and s over b. If they ever said to do it with the y-intercept, which they rarely do, you just change the variables to accordingly fit that. So you have your slope divided by your standard error of the slope. This is not given in the test, and a lot of times you'll get MCQ questions which will give you either your t-test statistic, your slope, or your standard error of the slope, and it'll ask you to find the third one or find an expression for the third one. So I would highly recommend memorizing this. And for your calculator, which this honestly never comes up, the questions they ask for linear regression generally be interpreting one of the variables in context, or finding your confidence interval, or finding one of the ways of representing your confidence interval, or one of your hypothesis or something like that. But you rarely have to do it, but in case they ask you, this is what you'd have to do, because sometimes they'll give you like 200 or 300 data points, and then you're gonna have to type in 200 or 300 data points into your thing, and it becomes very tedious, and it probably will take up your entire test just typing in those data points, and getting one wrong really blow your test out of proportion. And if you want to determine your association, we come back to R, which is your correlation coefficient. Next we move on to confidence interval, which is estimate plus or minus margin of error. You've heard me say this multiple times, but this time it's B plus or minus T star times SE of B. This you've heard me say for sure. With means, with proportions, you've heard. Again, slope and your standard error of the slope. Again, you don't really have to use calculated controls. I did forget to mention one thing when I was talking about hypothesis test. So when in the first unit, when we were discussing norm CDF, we were talking about how it's lower bound, comma upper bound, comma your mean and your standard deviation. However, for linear regression, or more importantly chi-squared, actually I'll put it up in the chi-squared section. So chi-squared, when you're doing the chi-squared, you calculate a control for any one of these. If they ever ask you what is your p-value, you would go and do chi-squared CDF, like we've always done, of your lower bound, comma infinity. Oh, that's not good formatting. I'll put it down below. Chi-squared CDF of lower bound, comma infinity, comma degrees of freedom. Now, why is it lower bound, comma infinity, and not lower bound, comma upper bound? That all of it comes from the diagram of your chi-squared. Earlier in the video, I said that your chi-squared statistic is always positive because it's squared. So because it's always positive, there are no negative values. If let's say this was your 0 point, this would be your 0 point on chi-squared, and it would be right skewed. It never reaches your left hand or less than 0 side. So this lower bound would actually just have start from the lowest possible value, which is 0. So the biggest chi-squared CDF you can get is 0 to infinity with some infinite number of degrees of freedom. And as your degrees of freedom increases, the chi-squared distribution becomes more and more normal. So if you had infinite degrees of freedom, actually doing chi-squared CDF of 0 to infinity of infinite degrees of freedom would give you the same as if you did normal distribution of 0 comma infinity comma 0 comma 1, which is very interesting to note. So I will put that again in my solved notes, but for now I'm going to leave it out for the fun part of the unit lesson. So I've given you two questions here and a subsequent question at the bottom. So for the first question, I want you to state what test it is. So whether it's chi-squared, test of homogeneity, goodness of fit, independence, or if it's a linear regression test. Your second question, I want you to do the same, but I also want you to conduct the test. And the third question over here is a three-part question that deals with linear regression model. So for the first one, go ahead and pause if you feel like you know the answer to this. So a company has a food stall with three types of food: Indian, Italian, Chinese. The table has the frequency of purchase. The boss thinks that these food types are equally favored. Is the boss correct? Well, my question isn't whether the boss is correct or not. My question is to state which of these tests these are. So firstly, we need to realize what type of or how many variables and how many populations we have. So in this case, we have multiple populations because we have Indian food, Italian food, and Chinese food, and we only have one variable. So one variable, multiple populations. So if you remember that from above, that refers to a chi-squared test of homogeneity. Hopefully I spelled that right. Next, the statistics teacher wants to know if students who eat 3 meals a day also play sports. So I actually have to edit the question a little bit, so I'm going to pause and do that. Sorry, the question was fine as it is. I just read it wrong. So this is very important to note because it is looking at how many variables are there. There are two variables, so two variables, and it's still one population. And we're checking if students who eat 3 meals a day also play sports. So the keyword also lets you know that it is a chi-square test of independence. I know in this video I hadn't put the steps to creating a hypothesis test, and I did that on purpose because we've done it for 2 units, so I think by now you should know the key fundamentals of how to do it. So I'm going to copy paste it from the proportions unit, and I'll bring it back here if you still need a refresher. I have tailored the method to create a hypothesis test a bit for the chi-square. So whenever I just told you to write down the z-value or t-value, I just meant find the test statistic. So first of all, state the test, which is, we figured out it's a chi-squared test of independence. Check conditions. What did we say the conditions were? Firstly, it has to be counted categorical. Counted categorical, these are counts and these are categorical. 3 meals a day, sports, yes, no, yes. So we say yes. Next one was an SRS and n less than 10% of the population. I didn't say anywhere in the question that it was, so if I never state it, you always say assume yes. That's how you can continue on. Next one is expected is greater than 5. So for now, because I can't use it greater than equal to, I'm going to say greater than or equal to 5. Greater than or equal to 5. Now, how do you find the expected? What did I tell you earlier on in the video? you anyway will always have to conduct your test. There's no way that the AP statistics board will give you a question without asking you to conduct the test. So conduct the test first and then come back to check your condition. I write down my formulas, right? So firstly, it's my hypothesis. So first A, the two variables which are playing sports and eating 3 meals a day are independent. So that means B equals 0, right? And my alternate hypothesis would be they're not independent. So B is not for this. I'm thinking of another question. Playing sports and eating 3 meals are not independent, right? We can't say dependent. Next is to find my chi-squared statistic. But before that, you need to write down the formula for chi-squared statistic, which is squared equals the sum of all your observations minus your expected value squared divided by expected value. That's good enough. Find the test statistic. Remember, I've said this time and time again, unless you see a follow-up question asking you for your test statistic, this is not really required. And now since we're in the independence portion, we're going to conduct our test. I'll put how I did on the TN's part first, and then maybe you can pause, do it for yourself, and then finally make sure that this expected is greater than or equal to 5, and then write down your p-value and conclude. Actually, I created a matrix, which is a 2x2 matrix, and gave it the variable ABC. The values I got were from this, which is very helpful. I could have had, in my matrix, I could have kept it as 14, 7, 24, 18. It doesn't matter as long as the rows and columns are in the correct order. I couldn't have had 24, 14, 18, 7. Then I went into my chi-square two-way test and put ABC, which is what I saved the variable name as, to my observed matrix. I come here into my values and I get the title, my chi-squared statistic, which if they asked for I could now show, my p-value, my degrees of freedom. Next, if I wanted to find my expected value matrix, this would be it. And if I wanted, when I went back to check my conditions, I would have to say yes, and then I'd have to put my picture of my expected value matrix. So I'd have to copy these values down and show that they are all good. Let's write down my p-value. So my p-value is 0.466, which means it's a high p-value. Do definitely please try this yourself. High p-value, failed to reject, null hypothesis, sufficient evidence that, and then again go back and copy my alternate, that playing this is true. So this just means sufficient evidence that my alternate hypothesis is true. The question is a linear regression test, a linear regression question. So here we have our constant, which has this value of 0.234, houses sold, which is 1.9, my standard error for constant and my standard error for my houses, and this is basically for now. You need not know what it means. My p-value for constant is 0, and for houses sold is 0.351. Now what's my first question asking? Create a regression model to predict the revenue in thousands. Okay, so we know how a regression model is based. It's your prediction equals your y-intercept plus your slope times your x. So what am I trying to predict? I'm trying to predict revenue in thousands, which is equal to my y-intercept, which is constant, which is 0.234, plus my slope, which is 1.9 times x, where x is my, so I can put it into the next line, x is, lowercase x, houses sold. Now create a 95% confidence interval. So as we remember, our confidence interval, maybe you need a refresher. So just quickly look back up and come down. Plus or minus b plus or minus t star times your standard error of b. Now the question should have been create a 93% confidence interval for the slope, which makes more sense, otherwise it's very ambiguous. So b is what is our slope. It is 1.9 plus or minus t star. Find t star. Now you could go inverse t and do how you normally would. So I'm just gonna put it in here as inverse t, and 93% is 0.93. Unfortunately, the question doesn't say degrees of freedom. Since it doesn't do that, we actually can't use inverse t. We need degrees of freedom. So what we do instead is we assume that it has an infinite degree of freedom. What we'll do then is that we'd use inverse norm of my area, comma my mean, and my standard deviation. So you may or may not have caught it in the previous video, but I stated that when you put an infinite degree of freedom for your t star, it becomes a normal distribution. So this inverse t, so if I just write it here, we don't use t star because we don't know degrees of freedom. We use a conservative estimate of infinite degrees of freedom, which enables us to use inverse norm, right? Infinite degrees of freedom. That will allow us to use inverse norm. This question was just badly worded, but in normal situations you would get your number of trials or data points you have. We have inverse norm, and now we just have to multiply it by our standard error of our slope, which gives us this. So you write your confidence interval in this portion, and that comes out to be something like this is your confidence interval. You should also draw a diagram. I will leave that drawing to you. Again, depends on how you round, your answer will differ, but your value should come out to be 2.490316 and 1.309684. Something along those lines is perfectly acceptable. Your rounding is just based off how you would do it. Section or part C. You wish to determine whether or not the two variables have a positive association. Two variables in this case are houses sold and revenue in thousands. State the null and alternate hypothesis and state your conclusion in context. Do not conduct your test. That is very useful because if you wanted to conduct your test, you would have to know a couple more things. You'd have to know exactly what your degrees of freedom are, and you can't use inverse norm, norm CTF for that. You could, but your estimate would be really off and it becomes very tedious. So let's just look at null and alternate, right? So null hypothesis is that the two variables, which are revenue thousands and houses sold, have no association. So b equals 0. I would recommend you write beta, but I'm not going to do that because I'm trying to get a point across. And my second part, which is my alternate hypothesis, is that revenue in thousands and houses sold have a positive association b greater than 0. How do I know it's positive association? Well, it's in the question. So I've answered one part of the question, and I state my conclusion in context. But how do I say my conclusion without conducting the test? That's what this part is for. Since it's talking about the slope, you would look at the p-value of the slope. P-value is 0.351. P-value, p-value 0.351. What does that mean? High p-value, fail to reject the null, and sufficient evidence that, or rather, to try insufficient evidence that the alternate is true, that bingo, that revenue in thousands and houses sold have a positive association. Maybe if we had more data, we could actually see that, but this is what our regression model indicates. These numbers actually don't make any sense because, as you can see, the slope is positive, and we have something like a negative, or sorry, a p-value which indicates that they don't have a positive association. So the question's faulty, but we're gonna go along along with it, because that's how questions are. This isn't a philosophy class where you can question the question. You just go along with the data given. I should have actually put this to be 0.0351 because that would make more sense. Anyway, thank you so much for watching the past 7 videos I made on AP statistics. It's been a great pleasure to have you guys as an audience and to create the videos. I'm hoping you guys have learned a lot from my videos and continue to use your statistics knowledge further in the future somewhere or the other.